Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will implement a variational autoencoder, right? So in previous video, we had understand how variational autoencoder works, right? So if you haven't checked out that video, please go back and visit that. It will help you to understand the code which we are implementing in this video, right? So just giving a brief about the variational autoencoder. So it is similar to our autoencoders, but it will use to generate a new images, right? Which is similar to our training point. Okay. So in encoder, instead of this mu and sigma square, we were using a latent dimension vector and it will be passed to a decoder. But in variational autoencoder, we are calculating a mean and variance from the encoder outputs, right? And we are sampling a new vector using this mean and variance, right? So that sampling output will be passed to the decoder to generate the output, right? And as a loss, we will use two kind of loss here. The first is scale divergence, which will basically compare a distribution, right, in general. So here, using this mu and sigma square, right, we will calculate how this distribution is near to normal distribution, right? Because we want this mu and sigma square from the normal distribution, right? So that's why we will use scale divergence, and second will be our mean squared error, right? Which will basically mean square between input and output. Okay. So let's get started. So first I had imported few libraries. Okay. So let me run. Okay. And just I imported a MNIST dataset here. Okay. And just converted into the shape of 28 cross 28 cross 1 because we need to apply a convolutional neural network, right? Okay. So let's start. So let's implement this sampling part first, okay? In the previous video, we had understand while generating a samples, we will use the formula like mean plus sigma times epsilon, okay? But epsilon will be a random normal variable from normal distribution, right? So let's write that because we need to only optimize mu and sigma square, not that epsilon, okay? Let's write sampling. It will take some arguments, right? What would be that arguments? Argument would be a mean and let's say log variance, okay? So instead of variance, we are using log variance here, okay? Let's say arcs, okay? So this mu and sigma square are here, okay? Now let's extract the base shape, right? What will be the base size? Because we need to create a latent dimension, or you can say samples according to base size, right? So let's say base size is equal to, we can say k dot shape of mean of 0 because at 0 we have base size, right? Let's say latent dimension will be, okay, here it will be equal to, right? Let's say latent dimension is equal to, we will use int shape, right? Let's say z mean and we will extract the 1. So when we use k dot shape, it will return a shape with base size, right? And when you use int shape, it will not return a base size, okay? So it will return a output size, okay? So let's say z mean of the 1, okay? So let's say now we need to calculate epsilon, okay? Let's say epsilon is equal to, we had seen that we need to create epsilon from the random normal distribution, right? So let's say k dot random normal shape will be base size comma dimension, right? Now let's say return, we need to create that, right? So let's say z mean plus, we have variance here, right? But we want to use sigma, which is standard deviation, right? So let's say 0.5, okay? So now into epsilon, okay? So this was our sampling function, okay? Now let's define encoder, okay? Let's say encoder. So before implementing encoder, let's define few variables which we will use while implementing encoder and decoder. Okay, so first let's say input shape, right? It will be encoder's input shape basically. So it would be image size. So image size we had seen it is 28, right? Let me write here. Okay, so you can see here is 28. Okay, so let's say image size to image size comma 1, right? Because we had one channel out input, right? And output will be also one channel. So let's say batch size we will use 128. Okay, kernel we will use, let's say 3, and we are defining layer filters, right? So for each layer how many filters we will use, right? So let's say we will use only 2 convolutional layers. First will contain 16 features or filters, and other will contain 32. Okay, now let's say latent dimension, right? So for let's say latent dimension, we are just want 2 dimension as a latent dimension. Okay, and we will train for epochs, let's say 30. Okay, so these are few variables we will use to implement. Okay, so now let's say inputs will be, let's define input shape will be input shape, right? Let's provide the name as encoder input. Okay, so spelling mistake is here, let's correct it. Okay, input shape is not defined. Okay, here we go. Okay, so now let's say x will be our inputs. Okay, now let's say for filter size in layer filters, right? And we can define convolutional operation con2d, and let's say filters is equal to filter size, right? Let's say kernel size will be defined kernel size, which is basically 3, right? And then let's say activation we will use relu. Okay, let's say stride we will apply 2 because we want to decrease the dimension, right? And let's say padding is equal to 7. It would be padding, right? And it will take input as an x, which is input size, and then this x, right, which will be the output of convolutional network. Okay, so now let's extract the shape of the convolutional neural network, which will help us in the decoder while we will implement the decoder, right? If you had seen the autoencoder implementation video, you can recall this. Okay, but I'll explain why we require that shape. Okay, so let's say convolutional latent space latent shape, okay, will be k dot int shape. Okay, now let's do flatten. Okay, so here till here we have output in 2 dimension, right, which will be the batch size comma in image shape into image shape or something like that. Okay, so because at each convolution we are converting our image size into half, right? So here maybe we will have the shape of 8 cross 8, but we will see when we will plot the model. So now we are flattening up our output. So now let's say x will be now dense. Okay, so let's say dense is 16, and we will apply activation will be relu again x. Okay, so now we need to calculate our z mean and z log variance, right? So let's say z mean we will again use dense layer here. Let's say z mean is equal to dense, and it will be a latent dimension, right? We are using only 2 size for the latent dimension. Okay, and let's provide the name as well. Let's say name is equal to z mean, okay, and it will take x as an input, right? Now let's say z log variance will be same, okay, same size of mean and same size of variance, right? Okay, it will also take this x because we need to derive mean and variance from the output of this dense layer, okay, right? So now let's apply a sampling method which we had defined here, right? This one, let's say. So for that we will use the lambda layer for the TensorFlow, which will allow us to bind our expression or function to the layer, right? So let's say z will be lambda. Let's provide the name of our function, right? And output shape. Output shape will be our latent dimension, right? Let's provide the name also. Let's say it is z, okay, and what it will take as an input, it will take z mean and z log variance, right? These two input we are expecting here, right? Okay, okay, so this is all about the encoder. Now let's initiate the model encoder. Okay, there is one error, keyword argument not understood activation. Okay, okay, the spelling mistake. Okay, still let me rewrite. Okay, it will be activation, right? In here also, that instead of stride it will be strides, right? Let's rerun. Again one error, Keras tensor object has no attribute dot lower. Okay, where we had provided the lower. Okay, okay, so here it will be like this, right? Flatten layer and input will be passed like here. Okay, let's rerun. Again new error, operation not allowed, exception encounter while calling layer to z. Okay, what is the problem here? Okay, so as an input we cannot pass two input, right? It should be one input as a layer, because here also we are expecting a list, right? Then we are extracting here, and same here as well. So let's rerun. Okay, so now it's working. Now let's initiate encoder model, right? So encoder will be, let's say encoder model will model inputs will be these inputs, right? Image size, and our output will be three outputs we will require: mean, log variance, and z. Okay, let's say z mean, z log variance, and z, right? Let's provide the name as well. It would be encoder model. Okay, let's plot this model so we can check the shape as well. Plot model, encoder model, show shapes is equal to true. Okay, okay, so here you can see we started from 28 cross 28. Now it size will be half, 14. Now again 7, and then after we had flattened this output and we get 1568, and then we apply dense layer which is a 16 dimension, 16 units. Okay, and from that 16 units we are extracting a mean and variance of 16 dimension, right? From the 16 dimension we are applying dense layer of 2, which will be our latent dimension, right? So as an output we are receiving 2. Okay, the mean and variance of shape 2, and then from that we are sampling our latent vector, which is again the shape of 2. Okay, so let's now define the decoder. Okay, let's say decoder. Okay, so decoder will contain input as an output of encoder, right? So let's write here latent inputs because it will consider this as an input, right, which is our latent dimension or latent vector. So let's say input shape, no, it would be the input layer, right? Input, let's say shape will be latent dimension, right, which is in our case 2. Okay, let's say we can pass the name decoder input. Okay, it will be deep. Okay, so now first we need to convert this 2 dimension into 16, because decoder is an inverse process of encoder, right? So we will start from 2, then 16, then this 1568, then 7 cross 7, and so on, right? So let's say x is equal to dense. So first we will convert this 2 dimension into here, right, which is 1568. And how we will calculate this number? So if you see here, we had extracted a shape, right, before flattening. So we will use this shape and then we can provide like this. Okay, let me write it here. For dense dimension, we can use 0, let's say 0, it would be from 1, right? Let's say 1, first would be base size, that's why. So let's say 2 into 3. So basically we are doing 7 into 7 into 32, which will 1568, right? Now if we receive this dense layer, which is basically a flattened layer of size 1568, then we can convert it into 7 cross 7, right? So let's say x is equal to reshape, we need to pass a same this, right, but with not the star operator but the comma operator, right, because we need to reshape. So it can be 1 or 2, right? Okay, and the input will be x. Here also it would be a latent input, right? Let's say latent inputs. Okay, so now we receive the shape of 7 cross 7 cross 32, you can say here. Okay, so let's say now we need to apply convolutional layers, right, but we will use convolutional transpose operator, which will upscale the image, right, because we need to convert 7 into 14 and 14 into 28, right? Okay, so we will use the same layers but in the reverse order, right? We had defined here 16 and 32, but we will start from 32 because it is an inverse process, right? So let's say for filter size in layers filter, let's reverse this list. Okay, and we can apply like x is equal to quantity transpose, right? Filters is equal to filter, let's say kernel size is equal to kernel size, which is 3 in our case. Okay, let's say activation will be same, activation will be relu, strides will be 2, and let's say padding also same. It will be all argument would be same as a convolutional 2D operator, right? Padding, let's say same. Okay, it will take x as an input. Okay, so now we receive the output till here. Okay, so now we need to convert our channels, right? So let's say output will be quantity transpose, because the output of this will be has filter size of 16, right? We reach till here 28 cross 28 cross 16. So now let's convert, let's say filters will be 1 because we need a 1 channel output, right? Let's say kernel size will be kernel size, which is 3. Activation will be relu. We are not applying the stride, just let's say padding is equal to same, right? Let's provide the name as well, right? It will be a decoder output. So let's say name decoder output, and it will contain X as an output. Okay, so here we can use activation as a sigmoid because we are expecting output of the each pixel between 0 to 1, right? So it will be a sigmoid because we are pre-processing here as well. So if you see, we are dividing our image by 255. So basically our each pixel will have value between 0 to 1, right? So now let's run this. Okay, less than not supported. Layer filters, what happened? Let me print the layer filters here. It's 16 and 30, it is the same. Okay, so it will be a filter size here, right? Okay, let's see. Okay, it's run successfully. Now let's initiate a decoder. Let's say decoder model will be model, and it will take input as a latent dimension, or if what we have defined, it is latent inputs, right? Let's say latent inputs, and output will be outputs, this one output, right? Output. Let's say name will be decoder model. Okay, let's plot this as well. Let's say plot model decoder model, comma, show shapes is equal to true. Okay, right. So if you see here, we started from the 2, which is a latent dimension, and we are upscaling our dimensions, and we reach 28 cross 28 cross 1, which is the same shape as an input, right? So we can apply mean square error there as well. So this was about the decoder. Now let's initiate variational autoencoder, right? So our VAE will be model, right? And what it will take? It will contains a input as an encoder inputs, right? So let's say inputs, this one inputs, right? This. So it will take encoder input as an input and return the output of decoder, right? So let's say we will require only Z, right, which is a sampling output. So we can write here, let's say VAE output will be, let's say, decoder of encoder inputs, right? And we can take a second, which is third output, right? Let me write, it would be decoder model, and it will be encoder model, right? Okay, so if you see from the encoder, it will be like this. Okay, so what we are doing here, we are taking a third output of encoder, 0, 1 and 2. So 2 will be third output. Third output is our Z, right? If you see here, we are getting a 3 output, and Z is third output. So we would require Z because decoder will consider Z as an input, right? Which is the size of latent dimension. Okay, and this will be variational autoencoders output. Okay, let's say name is equal to VAE, right? Let's rerun. Okay, so now our model is defined. Now let's define our losses, right, which we will use. So we know that we will use 2 loss. First is scale divergence and second is mean square error, right? So let's define losses. So let's first define the mean square, which will also called as a reconstruction loss, right? Reconstruction loss, let's say MSE, mean square error, between let's say KL dot flatten, it would be inputs, right? Because we need to predict the images as size of input and similar to input, right? And the second would be k dot flatten, it would be 2t, right? K dot flatten outputs. Okay, sorry, right. Okay, so it is not outputs, it's the output, right? This one. Okay, basically output of decoder, you can say. So it will be our reconstruction loss. Let's say reconstruction loss to image size into image size. Okay, right. So now let's say KL divergence we need to define, right? Let's say KL loss is equal to 1 plus Z log variance minus K dot square, let's say Z mean. We are implementing basically this one, right? This one. Okay, so we had used like 1 plus log of variance square minus mean square minus this sigma square, right? Which is variance. Okay, so let's rewrite. So it is a Z mean minus K dot exp Z log variance. So we are using this exponential because we are using log variance here, right? So we need to use variance here. That's why we are applying exponential here. Okay. Now let's say KL loss is equal to K dot sum KL loss over the axis minus 1, right? And at the end we need to divide by 2, right? Here if you see the equation, it is minus 1 by 2, right? So we can multiply this equation using minus 0.5, right? Let's say is equal to KL loss into minus 0.5, right? So this will be our KL divergence loss, and now VAE loss will be sum of these two, right? So because there are multiple, we will use the mean, right? So let's say mean of reconstruction loss plus KL loss, right? This K would be capital. Okay. Okay, so now we need to add this loss into our model, right? So VAE is our model. Here we have defined VAE. So let's add this loss as well. Let me enter here. Dot add loss. It would be VAE loss, right? Let's compile this model. Compile. It would be, let's define this optimizer here, right? Optimizer, let's say Adam we are using. Okay, so this is about the variational autoencoder. The graph is disconnected, cannot obtain a tensor keras of shape 2. Okay, so let's see what is the issue here. VAE loss, K loss, reconstruction loss. Name decoder input, describe created by the decoder at layer 3 following previous convolutional 2D form. Okay, so let's see what is the error here. We are using this output and the same output we are passing here using VAE output, right? Okay. Okay, so here it will be VAE outputs, right? Not that output. Okay, so we need to use this variational autoencoder output, right? Okay, let's rerun. Okay, now it's run. We had changed the output variable here. Okay. Okay, now let's plot this model. Plot model VAE, and let's say show shapes will be true, right? Okay, so these are the laws we had added. It is multiple. So we started from the encoder, then there are some sampling layer, and these are the all the graph which we had implemented as a VAE, right? Okay, so let's feed this model. Okay, so let's say VAE dot fit x trend. We are not passing the y trend because we had added the loss accordingly, right? So let's say epochs will be epochs. Let's say batch size will be batch size, which is 128 in our case, and let's provide validation data as well. Let's say x test and none, right? Okay, so because we are calculating the loss between input and output of here, we had added the loss. Let me show you. So here we had defined the VAE output and inputs, right, and added that loss. So we not need to define here. Now let's fit and run this. Okay, so it will take few seconds. Let's define a function which can plot the output, right? So let's say define plot images. It will take, let's say, images as an input, right? Now let's say PLT, we need to define, let's say we will show 5x5 grid images, right? Let's say subplots 5x5. Let's say figure size will be, we are taking smaller size because our image size is smaller, right? So let's say 10x10, and it will return, let's say, axis. Okay, so one thing we can do, it will be in tuple, right? Fixed size. Okay, so now let's say axis will be axis dot flatten, it will be dot. Okay, now let's say for img image or axis in zip. So basically we are flatten that because we can apply a zip operator, or we can iterate over axis and one image at a time, right? So let's say images comma axis, right? So we can see like ax dot imshow, right? As we are applying PLT dot imshow, we are using axis, so we will apply ax dot imshow here, and it will take image, and let's say cmap is equal to gray, right? And after the whole grid created, let's apply PLT dot show. Okay, so this will be our plotting function, right? Okay, so let's see. Okay, so we can see loss is decreasing. We had started from 57 and now we are at 39 point something, and the same validation loss is also decreasing, right? Let's wait for one more epoch, then we can test it out. Okay, so here we are reduced the loss very well, so we can, you can run it for more epochs as well and tune our convolutional operator as well, right, for better output. So let's see the output here. So let's say result will be VAE dot predict. So let's say we were applying a 25 images, let's say X test of first 25, right? it would be our result. Okay, so let's plot these results. Plot images, let's say result. Okay, so name plot images is not defined. Let's rerun this. I think we forgot to run this cell, right? Okay, one error. Figure set got unexpected output. Fixed size. Okay. Okay, I think it don't contains the underscore, right? Let's see here. Where is it? False, squeeze, height, parameter, shape, axis. I think it don't contain the underscore. Let's remove that, right? And let's replot. Yes, so it works. Okay, so these are the few images which generated, right? So there are a few images which are blur, but yes, we can improve our convolutional operation, as we know that we had only used 2 dimension as a latent space, right? So we can improve that as well. We can improve filter size, convolutional layers, and this output can be improved. But this output is not bad, right? It's generating very well. So let's see the input here, right? What was the input? Let's say X test first 25, right? See 7, 1, 7 are generated pretty well, right? So this was the input what we had provided, right? 7 to 1, and we receive here 7 to 1, 0, 9. Okay, so here one thing. So if you see for the fifth image we had provided 4, right? But it generated as a 9, right? Because we are using variational autoencoder, and it will use random sampling, right, from that mu and sigma. It doesn't have the information like which digit we want to generate, right? So this is, you can say, one disadvantage of variational autoencoder, in which we do not have control over output image, right? As you know, we had provided 4 but it generated 9, and you can see like 4 and 9 is similar, right? Same, you can see here we are providing a 9 as an input, but it is predicting a 7 as an output, right? Digit is correct, but we are not controlling which digit we need to predict, right? So overcome this challenge, there is a one type of variational autoencoder which is called as a variational autoencoder, right? So in that we will provide the information that which digit we need to predict, right? So in next video we will implement that conditional variational autoencoder. So all structure will be almost similar, just there are few changes which will allow or let the model know that what digit we need to predict, right? So for this video, this is all about the variational autoencoder, right? If you have any doubt or query, you can write it down in a comment section. We can discuss there, right? If you like my video, please subscribe my channel and press the like button, right? We will meet in the next video. Thank you.